tutorial. And now we're going to cover the final airborne instrument that was part of SnowEx. This is the main instrument and the reason for the time series, Uavsar, which is an L-band INSAR. I'll let both Zach and Jack talk to us about that. But just while people are trickling in, I think it kind of got lost under the COVID announcement, but I did sort of throw out a question of what folks felt like they felt like a hack meant to them. So we talked a little bit yesterday about, asking around the community what you guys all felt like SnowEx meant to you. I was kind of curious to hear what folks thought a hack really meant to you. And I really liked Stephen Pastana's response, one of just the two responses from this morning, if you want to read that. But like a clever fix, right, where you maybe don't have all of the materials or resources that would do it in the most efficient or most effective way. And he mentioned MacGyver, the show, a character that was able to fix things with, a shoestring and a tennis ball and some duct tape or something like that. And so I think it's one thing to think about as we go through these tutorials. It's overwhelming. It's a lot of information. Again, it's a toolbox. It's a place that you can go back to. And I think the most important thing is to be able to kind of have an overview of what's available and the ability to go through this material on your own if it's going to be useful to you in your research. So I'm really excited about this next tutorial. This is Jack Terracone, a PhD student at University of Nevada, Reno, and by Zach Keskinen, a PhD student at Boise State. They've both been working a lot with this INSAR data, and I'll let them tell you a little bit about sort of the path that they started working together and some of the software products that came out of last year's SnowEx Hack Week. So I think it's one of our success stories and something that you could strive for is that something more than just the project, continues after Hack Week. The collaborations continue, and maybe you get to a point where you release a software package. So I'll turn it over to Jack and Zach, and thanks everyone for coming back.
Cool. Hello, everyone. I'm Jack, as HP said. I'd like to thank HP. None of this data would exist without him and sort of getting the funding and all that. I'd also like to thank Franz Meyer, who, if you want to learn about radar and INSAR, he teaches a class at the University of Alaska Fairbanks that both Zach and I and Naheem have taken, where really helps you distill a lot of this complex information, which we're trying to portray in this tutorial as well. Ross and Naheem have also helped us with the development of this tutorial when we were in Boise. So what is Uavsar? As HP said before, it's not actually a UAV. It's usually flown on a Gulfstream airplane, and it's a suborbital based INSAR instrument operated out of JPL. This instrument was sort of created and founded in the mid 2000s there, and it's been operating ever since. And one of the benefits of this instrument is that it works really well. They have a good full data processing team there to do the data processing for you, and you're going to get really consistent, nice results. As we've seen before, developing an instrument sometimes can be very, very challenging, especially in the radar field. So after the original overpass and one of the original flights in 2017, where we saw some really nice results between Uavsar phase and overall snow depth, that was enough to get two sort of nationwide US-wide time series campaigns funded in the winter of 2020, which was a 13-site campaign, which encompassed California sites, Idaho, New Mexico, and all around. So these were huge. A ton of data was taken on it, but that was unfortunately cut short during COVID. And then it was continued in 2021, more so in the Rocky Mountains and Idaho area here. And these are these maps, which you've probably seen before. We have information about all the site names. Dealing with the data gets a little bit confusing. They all have a 6-letter site name as well as where they are. So each flight line can be referred to as a lot of different things. But for each one, Grand Mesa, Boise River, when you're using our package, which I'll introduce in the future, if you want to search for those, you can just search by these names here within the package. The whole concept of UAV INSAR, which we'll go into a little bit more, is that this L-band radar, it's a sort of a lower frequency, and it's been showing to hold coherence a lot more. And in the future, we're going to have a satellite called NISAR, which is a TBD launch date. It keeps getting pushed, but it will be an L-band INSAR every 12 days from space. So this UAVSAR is a test case to show, can we use this technique suborbitally? And when it arrives from space, can we have this everywhere in the world every 12 days? So there are two main ways to access UAVSAR imagery, either from the Jet Propulsion Laboratory data portal, as well as the Alaska Satellite Facility. We probably recommend using the Alaska Satellite Facility portal to start with. It's much easier to use and it has everything you will need. If you want to sort of get into the weeds with sort of lower level data products that are hosted on JPL, we could talk to you about that. But I think to start, the ASF Vertex is the right thing to use. And then we'll talk about sort of data download and conversion. Sort of when we started working with this data, because this instrument was designed in 2007, that's sort of the way they have been putting out the data since that date. It is not updated whatsoever. So it comes in a binary file, which is not ingestible by any software, and then a header, or an annotation file, which is similar to an NV header, which gives the coordinates, but you have to do that all by hand. And in the beginning, we were like, how do we do this? I was really confused about everything, did not know how to project the data, do anything with it. And if we go to my tutorial last year, this is the amount of code that was just data access and conversion for here. And I was using it like 10 different packages. I had no idea what I was doing, never coded in Python, stealing code from Stack Exchange and getting it all done. And Zach was in my group last year and sort of was like, this is not the best way to be doing this. And that's when we started to develop this package called Uavsar Pi Tools, because the main sort of impediment to working with this data is downloading and formatting. And this package, which is hosted on a GitHub account on the SnowEx here, is just for, well, it seems relatively simple to just, oh, you're just downloading the data. It's doing a lot of things behind the scenes to create analysis-ready products for you. So there's a lot of different things that you can do with this package, and we'll show a little bit of it. But one thing too is that we've had an issue that is the NetRC. So we're working in a Jupyter Hub environment right now where all these things are configured for you. But say you want to go back to your local computer and you have to do a Conda environment, and you're going to have to do all this stuff to initialize to be able to do this type of work on a local machine. So we have a function in here that will create that NetRC for you when you feed it in your Earth data information. And then you'll be able to sort of use wget and all these other functions we've been using on our hub on your local machine as well. In this case, there's a lot of different ways you could generate URLs to download from. To begin with, it's easiest probably to just go to ASF Vertex, do a quick search. Say we wanted to go to UAVSAR here. Live mapping, always a little bit stressful here. I know the Jemez site, just because I've been doing work here, is, oh, that's Arizona, not New Mexico. See, is about right here. I could search for that. And then we get our grains over here, and then I say download file, copy link address here. In this case, we'll sort of, let's just comment this out. Do this. We'll copy this file into here, and this is for downloading a single UAVSAR scene. So in this case, we're importing our Uavsar Pi Tools. We're importing the class UAVSAR scene. We're feeding it a URL, a working directory. In this case, it's the temp directory on the hub that we're downloading into, and we're cleaning up after ourselves as well, deleting things that we don't need. We'll initialize the scene there and then go UAVSAR to TIFFs. We do not, if you're running this live, we don't have this in the notebook, just because last year when you hit these servers live with 70 people, everything breaks. So it should do a little progress bar here. It's going to download the data. It's going to unzip the data for you. It's going to format it to do all the NAND formatting and produce you a GeoTIFF and EPSG 4326 that can be easily read into ArcGIS, Python, QGIS, and be ready for download. While it's spinning here, up there, it's, it depends. Some of these UAVSAR files are quite large, many gigs, so they do take a little while to download. Another functionality of this, which we probably recommend doing, say you want to look at the Loman site or Grand Mesa or any individual site, you can just call it by the name of the collection that we had referenced before. So you just download one line of code and we'll download all Grand Mesa data in the Uavsar collection that's in the NASA DAC there. So this is the first time Zach and I are doing package development. It's very tricky and hard, but please use this and give us an issue on GitHub or tell us what we're doing wrong, or because this is a work in progress. We've just added more functionality to do really more in-depth Uavsar analysis that we don't really go over in this tutorial, but we're trying to keep adding to this for this to be a place for not only SnowEx people to use Uavsar data, but the broader sort of community of geologists and sort of, especially those are the main people who use it, like tectonic geologists and geomorphologists looking at Earth's surface deformation. So that's our package there. And then we'll go through and start talking about the imagery of Uavsar data as well. Yeah, so this is done. We should put a little done in here as well when it's there. All these little things. So I'm going to go over to the rendered version here. And is that a good size? Yes, it is. So here we have a little table of all the different data products you're going to get at Uavsar, which can be a little intimidating off the bat. But we're going to try in this Uavsar sections product slide to look at things and sort of try to understand them, or to begin to start understanding the data products and then how these can be used for snow applications. Because if you don't know what coherence is or amplitude or phase, when we start going in and doing all the calculations in our analysis, it's not going to make as much sense. So that's what we're going to try to do in this section. And then Zach will go through and show an analysis using these data products and doing snow estimation to end it. So we have an annotation file, which is just the metadata there. We have amplitude files, which are the amount of power that is scattered back from the ground surface to the radar. In an INSAR pair, there'll be an AMP1 and an AMP2 with both acquisitions on the ends of it. We have a coherence file, which is a measure of the noise level of the phase, or the consistency of the phase between the two acquisitions. An interferogram, which is a wrapped file, which just goes between 0 and 2 pi radians. An unwrapped phase, which is taking that interferogram, processing it through an unwrapping algorithm, which we won't go into a lot of detail on, but sort of explain some of the nitty-gritty of that. An incidence angle file, which is generated from the DEM below. These files are all also ground projected, which is a very important thing. There's something called slant range coordinates or radar geometry, where files are looking at it from like the radar and they're not put on the ground. There's a process of using GDAL warp and some other functionality to ground project them that JPL is doing for you. So it's important to, if you're ever using these, make sure you're using the ground projected files. And then Uavsar is also a quad pole instrument. So I have not personally been focused on the polarimetry as much, but you can get all 4 polarizations, VV, VH, HV, and HH within it. Within a lot of vegetation studies and sort of other disciplines than snow, they're really interested in this. And there's a lot of crazy math you can do with the polarizations that you can get into. But for our cases, for snow applications, we found the copolarizations, which are HH and VV, are probably the ones you should be using. I've been using HH and would probably recommend that for the future if you're looking at doing any snow application stuff. Import our libraries. At this point now, later in the week, we've seen a lot of these different libraries that we're going to be working with, so I won't go into a lot of details. And then this is sort of an example test case we're going to be using. The Banner Summit line, we have Boise, Idaho right here. And this whole line is called Loman, is the shorthand name of that. And the example plots I'm about to show you are just from this box I picked out over the Banner Summit region. And it's important to note too, the Uavsar is a left-looking radar. So it was flying from the northeast to the southwest here is the way this line was the acquisition on it. So which will be important when we start looking at some of these data types. Load in the rasters. Here we just want to show some optical data from this imagery, or optical imagery from this time period. So here we have, and this too, just a reminder, these data sets I'm about to show are of this blue block. That's right here, just the subset. Here we have some optical imagery. So what do we see here? We see some missing pixels. Those are cloud cover points there. I think this is a reservoir to HP and Zach, if I'm correct, right here. And then we have a road and just some tree terrain, some snow terrain as well. And understanding what's on the ground, what type of land surface is the radar wave interacting with is really important for interpreting your radar data into the future. So we have this image stream, just try to remember this, and then we're going to go through the same area again, but just with the different INSAR layers that you can get from UAVSAR. Read all this in using raster, or this is RioX array, convert it to a NumPy array, and then plot it. So we'll just do a range of plots. We can go through these sort of quick. We have our unwrapped phase here between 2 radians and -3 radians. And the areas that are white is where there is the unwrapping algorithm failed, or it was masked out. So these white areas are showing places where we're not really confident with the phase measurement. And I just want to note those as we go forward and how they sort of correspond with the other different types of interferometric measurements that we'll be getting. And then below this, we have a coherence plot. Again, coherence is a measure of the consistency of the scattering properties in that pixel between acquisitions. High coherence in the yellow here, and then low in the dark. And again, this same area, especially these are a lot of south-facing slopes, have lower coherence. The road right here is sort of low, but then there's some higher coherence in these north-facing slopes as well. This sort of, in these areas where you see this lower coherence area, we're probably not going to get good INSAR information from that. It's just something to note as you move forward. With that, we see an amplitude response as well. This lake, you get very low amplitude due to radar wave attenuation. I'm not sure if it was frozen or not, but either way, it's a very low amplitude. Again, on this south-facing slope, very low power coming back because of the really high noise low signal to noise ratio. And this sort of also corresponds with the elevation model we have here and the incidence angle. These incidence angles are very high, which means the radar is almost shadowed from the radar wave that it's looking at. And that's why these all correspond between a high incidence angle, low amplitude, probably low coherence, which propagates into not a lot of phase information there. So trying to understand, well, I'm just introducing this, it takes a while to start to understand these data types, how they interact, to be able to better sort of understand our snow measurements when they come out. And then we have a full comparison plot here, just a little bit of putting these all together where you can see them all in one space and start to look at them and just get a good visual on what you're seeing, and then the optical imagery as well below. And from here, I will pass it off to Zach.
Thanks, Jack. Thanks, everyone. Megan. It's a really good question. Jack, HP, you want to take that one?
If I had to guess, it would be that it's like a water bike, because it's so flat and smooth, and we're measuring at incidence angle, so mostly energy is snow long getting scattered away from the radar. Similar to the conveyor, but I don't guess it's just amplitude.
Any other questions before we keep cruising? No? All right, perfect. So moving down, if you don't have the rendered version up, you might want to pull that up because we're about to take a closer look at that. A little think, pair, share. So we come down here, we're going to look at our second site. This is in Northern California at the Sage Hen Creek area. And if you scroll down here, we've gone ahead and plotted the coherence on the left side of an image from an image pair, where the first image is on the 20th of December and the second image is in the start of January. So a coherence image, that's basically a measure of the image quality. If you zoom in, this topo map actually gets somewhat reasonable. I want you to grab a partner. I'm just going to take 5 minutes here. So come back at 1:10 and just chat with your partner about what impact are lakes having on this coherence, what impact are the different aspects having on this coherence, trees, and why might that be? What do you think it is about those features and the snowpack that we can assume is here in late December that might be causing those things? So chat away. I've made a mistake. I've made a fundamental error in what I'm doing here. All right. Does anyone have anything they noticed? Ross, what'd you see? Give us your thoughts.
Well, I saw that the coherence seemed to be really low in the places where there are lakes or other standing water.
Do you have a guess on why that is? I guess you probably know, but.
Yeah, I'm guessing it's mostly that any incident radiation there was probably either absorbed or if it was reflected, it was reflected away from the system.
Yeah, probably absorb, right? So wet snow is another thing to think about there, where wet snow really easily absorbs a lot of this energy, causes low coherence. What else? Anyone else have anything else they want to toss out? From the back? Quinn, what'd you see? Yeah, so I think that's a great point. If you scroll down, I know elevation is a little hard to look at. So I plotted the coherence of the different elevation bands. So you can see as you get to those higher elevations, probably expect a little bit more snow there. You have a lower coherence. The road definitely had low coherence. Aspect wise, anyone have anything on aspect that popped out to them?
Yeah, the south section north has a different kind of appearance. You peek at the head and say, how the geometry hits the surface.
Yeah, so the incidence angle, right, and those very steep incidence angles. Also, if you start to see those south slopes really disappear, it could be snow melting, could be starting to get some wet snow in there. Probably not in this one, but that's definitely something to think about. And I think this really shows, this is something that I do on almost every image that I have to look at. I just start by looking at the coherence and saying, where am I actually going to be able to use this data? It's a huge limitation of this is, where is this going to be somewhere where I have a high enough coherence that I can actually get valuable information out of this? And that starts with just thinking about what's happening on the ground. What does it look like on the different aspects? What does it look like on the different elevations? And so if you scroll down here, this is not a, yeah, it takes a second to load. You can see that when we look at the coherence here versus the unwrapped phase, areas without any purple or red or whatever colors have been masked because they have too low a coherence. And so those are areas that we aren't going to be able to apply this SWE inversion technique that we're about to talk about. And so regardless of how good the technique is, this is one of the limitations you have to be thinking about and you have to be aware of when you're doing this, is look at your data, really get good eyes on it. Thank you for doing my thing, fresh air, I appreciate it. All right, so now we'll talk about how we're actually going to use this Uavsar imagery to try and learn about snow. That's what we care about, is how much water is starting to snow. Yeah, man. I can't promise I can, but I'll try. So that would be the change in radians between the first phase that returned and the second phase that returned. So it's what's the difference in phase between those two, which is a metric of how much longer it took or less time it took for it to hit that point and return to the sensor. You could think of it as a measure of the time of flight difference between those two, is a way you could think about it. Yeah. Other questions? Oh, all right, now I have to get back. All right. So the cool thing about Uavsar, the cool thing about this low frequency radar is it penetrates the clouds, but it also can penetrate through the snowpack. So we get information about the mass of water that's stored as snow in any particular spot. And the way we're going to do that is we're going to use this equation from a 2001 paper that uses the change in phase between the two image pairs, which you can again think of as a change in the time of flight between those two. It uses the incidence angle, and then it uses this dielectric constant that we're going to talk about a little bit more. But the basic idea is that when this radar energy is coming and it goes through the snowpack, hits the ground and returns, if we then add some additional snow on top of this, it's going to take a different amount of time for it to refract across that air-snow interface, bounce off the ground and return to the sensor than if we hadn't added that snow. So we can use this change in phase, this change in the travel time to try and get at how is the snowpack change between those two. So we're not getting the total snowpack, we're getting a change between these two images that we're looking at. So if we're looking at here, this delta D is the change in snow depth between the two. We have this change in phase. And then we have this lambda over 4 pi. It's basically a unit conversion. It's a way to convert from the radians that our phase is into an actual distance. What's the actual distance that we would want to think about those radians as? And then we have a complex thing on the right that I try not to think too much about, but it's basically a function of if the incidence angle, if it's a steeper slope and we add a little bit more snow, we're going to get a different change in the amount of time it takes for that energy to return than if we're on a shallow slope or a flat slope, where that incidence angle is different in some way. So then this last piece here is this dielectric constant of snow, and actually the real component of the dielectric constant, which is the measure of how fast radar waves move through snow. And for our purposes, that's as much as we need to think about it. And it's dependent on the liquid water in the snowpack and then the density of that snowpack. Question, yes? So luckily for us, JPL provides an incidence angle file that gives us that incidence angle calculated from the SRTM. But yes, otherwise you would need to calculate that yourself. Any other questions? No. All right, so let's get into it. So we've already downloaded the data. We are importing our database. I will point out that we've written in this Pi Tools, we wrote up that equation, and I would recommend using it. This depth from phase, we'll take a phase, an incidence angle, and an epsilon, and return a depth change of snow between those two. And I think it's a really nice function to use what's in there. I know that I have made mistakes trying to code up that really complex equation, and it's really nice to just have something that has had a lot of eyes on it. Jack and Ross both looked at it a bunch and checked it out, and it, yeah, hopefully isn't too wrong. So that would be a good thing to use. All right, so we're going to be using the February 1st image and the February 13th pass of Uavsar on Grand Mesa. So we're on to our third place up here. And I've just plotted up the coherence in the unwrapped phase. So again, the unwrapped phase is the phase difference between that February 1st flight and that February 13th flight. Yeah, yell out if you have questions. And this is just a little overview map showing where the bounding box is for Uavsar, and then sort of an overview of where we are. Hopefully everyone here has some idea of where Grand Mesa is after 4 days of presentations on it. So then we're just going to use the SQL database to collect some snow depths that we can use to calculate changes in snow that were observed in the field, snow depth that were observed in the field between those 2 dates. So we're going to query for depth on Grand Mesa that isn't GPR, because that takes forever. And then we're going to capture the ones that occurred on that first flight date, plus or minus 1 day, and then on that second flight date, plus or minus 1 day. Megan, I really like your list comprehension. I couldn't figure out how to do it, so I just did it this way. And then we're going to do this intersection. So we'll only be capturing points that intersected each other between these 2 days. So places where they looked at snow depth on that first flight and the second one. And then we're just going to subtract them to get the snow depth difference for each one of these field observation points. And when we plot this up on our overview map, you can see we have a nice distribution of points, and that we had a minimum about losing 5 centimeters and a maximum of gaining about 15 centimeters of snow between these 2 flights. So not a huge change, a lot of wind redistribution in this time period. So then the remaining parameters, we have to get incidence angle, this alpha value here that's on the bottom of the denominator. This fraction is provided by JPL. If you're doing the Uavsar collection that Jack was talking about, if you just include ints equals true, it's going to find and download the correct incidence angle file for every single image that you download as part of that collection between the 2 dates. So that's a really nice, handy thing that's hopefully useful. The other piece we need to get is this permittivity, this dielectric constant. If we assume that we have only dry snow, which for February is a pretty safe assumption, we can estimate the dielectric permittivity using this equation from 2001. So there's a variety of different other equations you could use just directly from the density. Again, we're going to use the database and we're going to look for snow pits that occurred on that first day. And we're going to go through each one of those snow pits. So the data frame.site ID there is the snow pit. And we're going to grab the top layer of the snowpack and extract its density. So we're going to average those densities and use the average density of the top layer of the snowpack. Do you have a question there? Okay, sorry. Again, the reason why we're using the top layer is we assume that it's probably most sensitive to the permittivity of that new snow that we're adding, and that the bulk density underneath it is probably pretty consistent throughout this time period. So that's why we're grabbing that top layer and focused on that.
How sensitive is the result of the permittivity equation?
Turn this over to HP again.
Yeah, it is interesting. I mean, there's a range of equations, and I want to develop the different dielectric sensors that were used in the snowpack. So it's a little harder to know what the instrument difference and what's more of a data difference. But I don't have it off the top of my head. On the order of, I would say, 5% of the model.
Awesome, thanks HP. That's why I turned it over to him. So we can get this mean density and we can estimate it using one of these equations. At Grand Mesa, because we're also interested in the liquid water content, permittivity was also measured directly. So we can also capture the measured permittivity for the top layer of the snowpack and compare those two. And when we compare those two, we can see that we're getting pretty comparable results from our estimate using just the density to what was directly measured in the field, which makes us both feel good about the estimation and that it was probably pretty dry snow during this time period. We don't see a big divergence of those two. It would make us think there's a lot of liquid water inside the snowpack. All right, look at that. So now we have our new snow permittivity, which feels really good. We have our incidence angle, our phase change. So now we're ready to do a SWE inversion and get that change in snow depth between the two, or SWE if you want to estimate density, since we have that as well. So I'm just, again, using this depth from phase that comes from this script inside of the Pi Tools package. And I'm just feeding in the unwrapped phase, the incidence angle. And in this case, I'm just feeding in density. So if you give this function density, it's going to automatically estimate permittivity and then do the equation that way. Or you can directly give it permittivity and it'll work on either a single value or a raster, whichever way you want to feed it in. So we have snow depth change, convert it to centimeters. And now we can just plot that Uavsar based snow depth change relative to the field observations that we captured from the database earlier. I put a little black backdrop on them to make them a little easier to see, hopefully. But it's still pretty hard to tell from this distance. So I also numerically compared them. So we have the field measured snow depths on the y-axis. Anywhere where there are multiple observations at a single point, I did the standard deviation as the error bar. And then the x-axis is the Uavsar snow depth change at that same point. So pretty good comparison. And we have a root mean squared error of around 8 centimeters for those two. There are ways that we can make this more complex and probably better, but I just wanted to kind of keep the basic idea clear of how we were doing things. So then the other piece that I did is I also did a comparison to the Lidar throughout this time. So here we have the Uavsar snow depth change, and we have the Lidar snow depth change. So this is the only site where we had 2 snow on Lidar measurements, so we could compare directly the change in snow depth as opposed to the total snow depth. So that was a good thing to be able to leverage here. And you can see that there's some areas where it seems like it's doing really well, some areas where maybe it looks like it's having a little bit more trouble. And I suspect if I had put the coherence on here, that would probably be a pretty strong correlation, and there might also be some vegetation effects that are driving those, but that's something that we're hoping to learn more about. And this is just an initial run through. And when we plot the Uavsar snow depth change versus that mean Lidar snow depth and the root mean squared, again, we get about 8 centimeters as our root mean squared error between the Lidar snow depth and the Uavsar snow depth. All right. Well, that's all I had to say. Thank you guys for listening. thanks to HP and everyone else for having us out here. Are there any questions? Sorry, you can clap now. All right, any questions we can answer? Yes, the question was to explain a little bit about the sensitivity of this technique to liquid water in the snowpack. Yeah, so liquid water in the snowpack has a couple problems with this technique. It tends to absorb a lot of the radar energy to have liquid water inside of the snowpack. And so that means that the coherence also tends to drop as a result. I don't think we have a full understanding of the relationship between the two of them yet. At least I don't, maybe someone else does, but I think it's a problem, and especially when you get to really wet snow, I think this is probably something where the technique won't work very well. So it probably wants to be used more in dry snow conditions in December, January, February, would be my intuition of it. Happy to pass to Jack.
I would say though, preliminarily, we've been doing some work. What?
I forgot about your work. Keep
Yeah, there is work down in the Jemez River Basin in New Mexico where we were seeing freeze thaw cycles in the snowpack. I wouldn't say, probably not full isothermal snow. And Uavsar was acquired about 9 a.m. and we held coherence the entire time. So is that probably giving us more hope with the NISAR 6 a.m. acquisition time that this could be a more robust technique depending on the acquisition of that radar? Yeah, I think so, yes. So there our permittivity values were about 1.6 there. There definitely was, when the pits were dug at about 11:30, the snow was wet. The radar was taken at about 9 and we held coherence the whole time. So I think more so in conversation with HP, it's probably a little more robust of a technique than we first anticipated, but defining and sort of understanding those breaking points of exact liquid water content, where is that within the snowpack? Where is liquid water? Those are definitely still research questions we're looking at and trying to understand.
Add one more thing.
Mhm.
Also, some of the tower-based studies have also shown that even when you have big surges of water, if it's refreezing, like Jack's saying, like at a 6 a.m. time period, the coherence seems to come back up pretty effectively. So you seem to be able to recover that coherence if it refreezes, is another promising result. Yeah.
But in addition to the coherence loss, there will be this change in speed. So we're going to interact with that for the models.
And have you explored like the
So you mean like when for the database analysis of looking at the top layer versus the bulk density? Yeah, so if we come back up to the top here, I'll let Jack talk about that too, but you can see here, a lot of the change is probably due to this additional layer here, and the speed change within this is probably going to have a big impact, more of an impact than the bulk density. That's probably going to stay pretty consistent as far as the speed it's moving through this snowpack here versus the same layers of snow.
But would you want to then you have to because would you want to look at the bulk density
I don't think you would need to have the change in snow depth. You just need to have some estimation of what the density of that is, because that's a parameter you have to back out to get that change. Okay, I must be misunderstanding your question.
It's okay. Maybe we can talk about it later.
Maybe Jack understood better.
Yeah, I guess that in this Grand Mesa example that we're giving, and two, I don't know if I probably made this clear enough. Grand Mesa is like the idealized place to do INSAR for snow. It's flat, it's cold, there's not a lot of ice lenses in the snow, it's pretty consistent. So these results look pretty good. As you go into more complex terrain, freeze thaw cycles, vegetation, this technique gets harder and harder and harder. So in this case, I think Zach's assuming that it didn't really change a lot, which I'm very certain that that's true. But in another case where there's like, we're working down in the Jemez where there was could be a lot of change or melting or other things, we probably would use this equation in a different way or do a more bulk density estimation. But we're still trying to figure out all that out about where's the spatial variability in all our methods, or one sort of way of using this equation and thinking about it may work in Grand Mesa, but that might not work in the Cascades or somewhere else. So I think we're trying to wrap our heads around that too, but that's a really good question because we've had this conversation before. Of what's the best way to do this, or how do we best think about these problems and use our equations to get there?
I will just add to that, you are fairly sensitive to density when you're calculating change in depth, but we're actually more interested in change in sweep, which are a lot less sensitive to in terms of choice of density that goes into the speed. So mainly we're focusing on depth because we've got a LiDAR data set in comparison.
Yeah.
If we had a full sweep map,